Hopefully this time you will receive the link to the video. I already share with you the folder, so if the video appeared, so it will be in the folder, so I don't want to share again new link. And the second query is that I already sent the link for today Google Meet, so please use this in future also anytime. So I don't know that there is any restriction for the number of the using a link or not in Google, but anyway, we use just only this link, so you can make this link as a bookmark in your computer and then or iPad, and all time just by clicking on that you will access. So you won't receive any new link from me. You won't receive any new link from me. That's all. This chapter today is the chapter 3. We will start chapter 3, but this chapter is very long and little difficult. You will have little difficulty for this chapter, especially the third part of the chapter. So first part of the chapter will be the review of the little about the quantum mechanics and modern physics. This will be do today. We will do that, but tomorrow, after tomorrow, the lecture will be little difficult. And we will continue this chapter and also in the next week. So 3 lectures we need to complete this chapter. At least 3 lectures, maybe it goes to 4 lecture. So anyway, next week you will receive a homework. I will send you the homework, some questions to solve. I hope you make a contribution to my lecture by talking and turn on your microphone and giving me your feedback. I already have a feedback of some of you, but please be more active. And one more thing I want to tell you that I think that's enough of what I say to you. That's all. So do you have any question or something, or otherwise I will start the lecture? If there is no question, just we can run the lecture. All right. I didn't see any query. So today's lecture is chapter 3. Chapter 3 is about fusion. So we want to go inside the star and see that what is the theory which we can use to explain the nuclear fusion. As you remember in previous chapters, if the temperature increases up to some special limits, then the nuclear fusion can be started. And we need a really special temperature, and we need it will be hot enough. Otherwise, as you remember, the star formation didn't complete, and the star, instead of to be a star, it will turn to the brown dwarf or whatever other cold star. So the theory which we use to explain the nuclear fusion is quantum mechanics or quantum physics. So you heard this quantum, especially recently, you heard the word of quantum computing several places. And also maybe you remember some newses some months before about the first running of a quantum computer, which it make a possibility for us to do the computations very quickly and faster than the usual computers. We are not going to talk about quantum computing, but I'm studying that. This is my research subject, but we are not going to talk about that. We are going to talk about the quantum mechanics, what is the quantum mechanics, and why we need quantum mechanics for the particles. And before to explain the model of the quantum physics, we need to explain that what is the size of the system which you need for them quantum mechanics. Because as you will see in the next slide, the physical systems have different size. We have a size of atom, we have the size of normal car, You have the size of astrophysical objects, and you have the long distances from your planet to the other planet. All are them in size. Even the time which passed from the Big Bang time to now, which is around 14 billion years, this time, giga year, also this time is also considered as a distance. We are going to talk about nuclear distances or nuclear dimensions. And then we say that instead of the Newton mechanics, instead of using classical mechanics, you need wave mechanics or quantum mechanics. And instead of the Newton law, you have a Schrödinger equation. But it will be very briefly. So I will show you that some mathematical notebook programs which one can use to find the solution for the Schrödinger equations. And then as application to astrophysics, mainly we are interested to know that how the quantum mechanics explain the nuclear fusion inside the stars. And this is the starting of our lecture, and we will end just in the beginning. Next, we will continue in the next lecture. What is the quantum mechanics? Particles are particles as long as you don't go to very tiny size. If the size of the system, any system, goes below some special numbers, then the quantum mechanics appears, and you need the quantum mechanics to get the result from the system. These diagrams, this figure I show always when I am talking to students about modern physics. The theory of physics are divided to the 4 categories based on the size of the system and the speed of them. If the size of the system is in the size of the planet or our size, and if the speed of the moving object is very, very low speed, then you need the classical mechanics. This is the theory which you can explain by them the motion of the old car or airplanes, planes, or any other things on your planet. What is happening if the system still has a reasonable size and big size, but the speed is increased? As you will see here, when the speed of the object increases, if this person who is riding or riding the bike increases the speed and turns to the particle, actually, you see that when the particle is moving with the speed of close to the speed of the light, and still the size of the system is reasonable, then you need relativistic mechanics, special theory of relativity. In modern physics, you are familiar with the special theory of relativity. This is a theory explaining the motion of the fast particles. If the size of the system goes down and below some special size, this special size is 10 power minus 9. This is the size of atom. If you are going close or less than this number, then you are entering the media, which is called atoms and molecules and that whatever. Still, if the molecules and atoms, electrons, protons, neutrons, neutrino, and everything moving not very fast, still if the speed is not very high, then you can use a quantum mechanics. So quantum mechanics, if somebody asks you what is quantum mechanics, you say quantum mechanics is a theory to explain the physics for the system with the size near or less than 10 power minus 9. This is 1 nanometer. And at low speed. Is it possible a system with the small size or tiny size moving fast? Yes, it's possible. If you want to keep the quantum mechanics, I mean, if you are going to study the system, the small size, and let the particle to move very fast, then instead of a quantum mechanics, you need a merging between quantum mechanics and Einstein relativity. So the theory, we call it quantum field theory. I would like to ask you, if you have a question, turn on the microphone and ask me, because if you text me, I cannot check your text. Can anybody tell me that, is it possible for the human or animal to move and to move with the high speed or not? What is going to happen for you, or any bacteria or anything, if it's moving or if you are moving with the speed comparable to the speed of the light? Do you have a theory about that? Because we say particles. Remember, the physics, classical mechanics, quantum mechanics, quantum field theory, and whatever is only about the particles. Several times, students stop at me and ask me about what is going to happen if we are moving with the speed of the light, or one person is moving with the speed comparable to the speed of light. Do you have any idea?
Maybe we're going
Yes.
to lose mass.
To what?
To lose mass.
The loss of the mass. Yeah, if the particle move with the speed of the light or close to that, basically the rest mass, or the mass which you feel, will be zero or vanish close to zero. I mean, what is happening for the body? If you don't think about particle, if a person, if a human or animal sent by the rocket to the place of the far space and let the rocket to exceed the speed, and let the speed be comparable to the speed of the light, what you think about what is happening for the body of that person, I mean for the inside of the structure? The answer is we don't know, because the whole relativistic mechanics and quantum mechanics and all works for the particles. You can go deep in this question and think about your body or any other animals or plants like a collection of molecules, and then you say that the molecules is composed by the atoms and atoms by the electrons, and so far if you need some biophysical argument to understand that, like bioastrophysics, this is a subject which is recently developed. It's about what is happening for human or living bodies when they are going inside the space. So we are not talking about any living body. We are talking only about particles. Nuclear dimension. What is the nuclear dimensions? The atoms are the basic elements in the universe, and you see the size of the atoms. If you consider the size of the atoms like 2 kilometers, the atomic nucleus, or what we call it nuclear size or nuclear part of the atom, is just some few millimeter of that. So there is a confusion in the literature, say that atomic energy or nuclear energy, that actually they are very different. When you talk about the atom, you can consider a very large size place with the size of 2 kilometers, as you see in this slide. And when you are talking about nuclear, is something in the millimeter in comparison to your kilometer. But the real size, what is the real size? The nucleus actually containing a number of the elements, we call it nucleons. Each nucleons, if you have a number of the nucleons like A, then it is possible to show that the radius of the nucleus, I mean the core of the atoms, will be proportional to the a power 1 over 3 cubic. This R0 is a number, is a 1 femtometer. 1.2, 10 power minus 50, it's called 1.2 femtometer. And remember that the volume, this is the size. So if you give me the number of the nucleons inside the core of the atoms, I can tell you how much is the size of the nucleus. The volume is proportional to R cubic, so you can see that the volume is proportional to the number of the nucleons. Okay? You know, remember what is A? A is the summation of the number of electrons and protons. Yeah? All right. If you have a density, then you have volume and you can calculate the mass. But I want to tell you that that's not very easy, because the density of the nucleons and density of nuclear matter is not very easy to estimate. It's not constant even. It is changing by the material form and also changing by the size of the nucleon. All right, so from this slide, you have to always remember that atoms is much more larger than in the size, larger than the nucleon. The person who was thinking about to model the dynamics and mechanics for the atoms, so many people work actually on that idea. So it was started by some experiment. It was started by some calculation done by Max Planck, and he was trying to explain the radiations. And Bohr, for example, the Niels Bohr was also Danish physicist who was thinking to explain the structure of the atoms and to say that why the atoms are the basic elements of the all matters in the universe. But the person who made this quantitative was Erwin Schrödinger. Schrödinger was familiar with the wave mechanics. You know that the wave dynamics is very dominant part of the physics. It is useful to explain many phenomena in physics using wave equations. One of them, as you know, is the wave, water shallow waves in ocean, for example, or every other things. Schrödinger was trying to write an equations similar to the wave equations to explain the possibility or to explain the structure of the atoms. The equation which Schrödinger found was an equation which we call it Schrödinger wave equation or wave equation. And this is the fundamental equations to explain the mechanism and to explain the mechanics and dynamics of the atoms and molecules and any system in the size below the 1 femtometer. If you have a system, the system is built by the atoms. If you are going inside the nucleus, so inside the nucleus at the distance of 10 power minus 15, the force is very strange type of the force called strong nuclear force. You know that everything with the charge is subjected to the Coulomb force. Atom has some electrons with negative charge, have some protons at the core with positive charge. So according to the physics 2, you know that they are attracting each other by the Coulomb force. By the Coulomb force is work only if the distance is around 10 power minus 9 or 10. If you go inside the nucleus, if you are going to talk about the nucleons inside the core, then the force is not Coulomb, it's strong nuclear force, And it is very strange type of the force, and I want to tell you that the strong nuclear force is not discovered very well, even today. But one thing about the strong nuclear force we know is that if the size increases a little bit, and it will be increased more than 10 power minus 15, up to 10 power minus 9 or 10, then strong force can be neglected. And if you neglect the strong nuclear force, still you will have a Coulomb interaction. In quantum mechanics, if you have a system, the first things you have to do is that to identify the potential energy. When you identify the potential energy, you can substitute the potential energy in the Schrödinger equations, and hopefully if you can find the solution for that, the solution is called wave functions. Wave function is a complex functions. It changes by all the coordinate in your system. For example, if you have just one dimension of the R, if you think about the atoms like spherical objects, you know that in spherical symmetries or spherical systems, like the Coulomb force or the one charge, you need just the distance. So R is the only coordinate which you can use as a position, and there is a time there. So position and time are the only parameter if you think about a system with one coordinate only. For such system, you can solve the Schrödinger equation. Basically, the Schrödinger equation is what is written here. But the problem with atomic systems is that they are not one, actually. Even the hydrogen atom made by the hydrogen and the proton, and each one has a different mass, yes? So you can see that it looks like that you have you need a two mass, one for electron, one for proton, and you need also two wave equations. And each wave equation gives you the possibility for the electron or proton to move according to quantum mechanics. This equation 3.1 is a Schrödinger equation. It's called a time-independent Schrödinger equation. By solving these equations, and there is only one coordinate here, R. The R is the distance from the center to any other points. If you can solve this equation, the solution of this equation gives you wave functions. And wave function can be used to explain the concept which we call it density of the particles. This is the first page of the paper published with the Schrödinger. And in this paper, which is written in German and later translated in English, he explained that why there are so many similarities between the classical mechanics of the wave phenomena and the atoms. And it is a fundamental paper in the history of physics. All right. When you have a potential, you can solve the wave function. Wave function is a complex function. It is a complex number. Complex number doesn't have any meaning in physics. Yes? By complex number, you cannot measure anything. The complex number means the root of -1. So the things which make sense is probability density. This can be obtained if you just make a square of the wave functions. The probability density of finding the electron, if the electron is prepared with the wave function called psi s, this is a psi or psi, at the distance of r to r plus delta r is given by that. I mean, this is a probability density or probability distributions. In statistics, you know that if you collect some people in the one room, so there is always a probability to find some people with the weight of less than 50 or more than 70, for example, if your sample is large. Also, there is no any chance to find a person, I mean the adult person, with 20 kilogram weight. What does it mean? It means that in the atoms you have several electrons. There is a possibility to find electron everywhere, not in special orbits. This is the difference, the main difference between quantum mechanics and the old physics before Schrödinger equations. Electrons are not classical particles to orbiting around the atom in special orbits. No, they are the particles which they can be everywhere and they can exist everywhere. Why it makes a difference? The difference is that some of the electrons had more chance to be detected in somewhere, and some of them doesn't have any chance to be detected. I mean, to show this, I want to show you a simulation did by the Mathematica, which is very useful to understand. This is the Mathematica. So look, this is a code actually. So the wave function for many systems is given not only by the R and T, it is actually three-dimensional, because as you know, the atoms or any other systems is in the 3 dimensions. You have a 3 dimensions and you have a quantum numbers. I mean, each place around the atom correspond to a special wave function. Yeah, and some wave functions correspond to more than one set of the numbers. So those we call it quantum numbers, or in chemistry we call it this. What is the name of these quantum numbers in chemistry? Anybody know? Orbital numbers, huh? Orbital S, orbital P, orbital D, orbital sp1, sp2, sp3, and so forth. For example, in these simulations, let the quantum number be, for example, the principal quantum number be 2, and let the radial quantum number be 0, 1, and let the azimuthal quantum number, those terms which I say, correspond to different forms of the electron around the atoms. You see, if I change in the quantum numbers, this 3-dimensional picture will be changed. What is this 3-dimensional picture? This is the distribution of electrons around the nucleus, okay? And what we call it orbitals. Psi 210 means that it is a wave function for a quantum level with principal quantum number n, this is the orbital number, and with angular quantum number 1 and the azimuthal quantum number 0. All right. You can change the quantum number even to higher quantum numbers, like when the orbit is run as 5, and when the orbital quantum number is 4, and when the azimuthal quantum number is, for example, 0. You see that the distribution of electron will change. What does it mean? What does it mean, those pictures? Do you have any idea? What does it mean, those 3-dimensional objects? Those are, as I mentioned, those are distribution of electrons in the atoms. I mean, if you go to the laboratory, you cannot find a single electron. What you will detect by the detector or by experimental tools is the clots of the electron, clots. Clouds of electron means such shapes. So such shapes or such clouds are the only things you can observe really about the electron. So in quantum mechanics, electron is not a particle. It's actually a collisions of collections of the waves. You know that quantum numbers can be changed as you see in different orbitals. You know, it can make a different orbital. Different distribution of the wave functions. But do you know, it is difficult to find those distributions. Those distributions need to solve the Schrodinger equations, yes, and find the distribution functions or find the part of the wave function which is depends to all the coordinates. I mean, if you have a 3 coordinates, so the wave function will be function of all these 3 coordinates. As you see, each coordinate has a one quantum number. Any question? Okay, this is very important. So I want to summarize. If you solve the Schrodinger equation, I mean this equation, for any system by knowing the potential, which we will do for the inside diffusion reactions, then you will get the wave functions. Using the wave function, you can find the probability density, or what is called PX. PX is just psi star times psi. And if you integrate this psi star psi psi, then you can find the probability. I mean, let me to know the wave functions. Then where is the electron? Electron can exist or be in any place in the space. It's not only at the distance of 10 power minus 9 or 10 power 10 or 10 power whatever. It could be existed everywhere. So if you can find electron between x1 and x2, you have to integrate this psi star times psi spec to x. And by integrating that, which we will do that next lectures, then you can find the probability. Okay, if you can find somewhere, I mean, if you can let me know 2x, x1, and x2, which gives you the probability of 80%, it means that those 2 points are most probably place to finding the electrons. Do you think which distances is the most probable place to finding the electron in atom? What kind of the size you think? If you go far from the nuclear, do you think your chance to detect the electron is increasing or decreasing, and why? Is it hard, this subject? Because no one communicated to me, and that's very...
Hello, doctor.
Hello.
Hello. When we go far from the nucleus, I think that the probability of finding the electrons, it will be decreased.
Why it will be decreased? Do you know?
Because I study in the chemistry that about electron map density.
Orbitals, huh? Map density.
Yes.
Okay.
Yes, it is
One
about.
reason. Yes. The reason is most probably to find the electron close to nucleon. Yes.
Yes.
For example, if the close means 10 power minus 10, I mean 10 power minus 10 meter.
I think has the radius. That's power.
Yes.
I think
Exactly.
5 to 52.92. I think like this number.
Yes, 0.58. Yes, exactly, angstrom. Good. This is the most probable place to finding the electrons. But you are talking about the hydrogen. Yes, it is about hydrogen atom only, because we are talking just about hydrogen atom. If your atom be very complicated, like with multi-electrons, like lithium, for example, yes, so then the wave function is very complicated. Even we cannot solve the Schrodinger equations. And then we need another technique like ab initio and whatever. But anyway, every time what you say is correct. If you go far from the nucleus, then the wave function, it looks like the wave function becomes weak. And these clots which we talk about, we call it orbital shapes or orbital forms, it will be very condensed only if you are close to the nucleus. And if you go very far, it looks like you don't see the clouds. Sky will be blue. If you look the whole sky, it's very rare to see all the sky with clouds. Yes, you see somewhere with clouds and somewhere blue if you look. But if you just focus on the places which there are clouds, you see the more density, and this is the place which the electron existed there. I want to show you again another mathematical notebooks. In these mathematical notebooks, people talk about the wave functions for hydrogen atom. It is a code there. It is written. The code is not very easy. Anyway, but using this code, what we can do? Using this code, you can generate the wave function, the psi. If you give me the quantum numbers, I can give you the density distribution of electrons in the orbitals. The one who is from chemistry, and most of you know that the orbital S is correspond to the quantum number N1. So this is the lowest level of energy, lowest or closest orbits to the atom, yeah, orbital S. Orbital 1s, if I set 1 n as a 1, and of course there is no L here, L is radial quantum number, so this is the density. What you understand from here, this is the wave function, okay, this is R. And R squared, this is the probability. So you see that it shows you that finding the electron close to the center is very rare. But the probability will increase up to somewhere. So the maximum chance to capture electron is where the radius, of course, versus the some number, because we have atomic units, like radius is not 1 or 2, you know, it's 10 power minus 10, 10 power something, 2 10 power 10, 3 10 power 10, and this. So it make it scale it here. There is a possibility to find them to capture most of the electron at a spatial distance. So this is the maximum chance. The maximum chance will be here. And then the chance will be decreased. And as you mentioned, if you go far from the center or from the nucleus, the probability will decrease. What does it mean, probability? The chance to get the electron will decrease. It is not only for first level. I want to talk about level 2, for example. If you say about level 2, for level 2, there is a 2 possibility. One possibility is orbital 2s when you kept the symmetry. This is called orbital 2s in chemistry. So here the probability is very strange, you know. First it increases up to the then, and then decrease it, and then it will vanish. I mean, for the level 2 of hydrogen atom, there is some place which you never ever can find the electron, and those places are the places when the probability is 0. The question which I will give you is that, for example, I will give you one of these diagrams as it is in the book, and then I will ask you to explain that. What is this maximum and what is the minimum when it will be 0? The maximum point, the peak here, show the most probable positions to finding the electrons. You have a 2 possibility. So electron can be captured in 2 places with highest probability. I mean, maybe 100% you can get the electrons close to these distances, here and here. But there are a place here which there is no any electron. I mean, as I mentioned, the atoms look like the whole sky. Some places are blue, some places are cloudy. For us, the cloudy place show the existence of the electron. And as again you mentioned, if you go far, the density will be decreased. All right? But level 2 has a different story. There is a two possibility. There is a possibility of level 2 when the second quantum number will be 1. This is called orbital 2p. Orbital 2p has this kind of the wave function, and this is the probability of finding the electron. And you see that orbital 2p very, very much looks like 1s, if you remember. And that is very interesting because it again shows you that the probability of finding electron will increase up to somewhere. So there is some radius which electron can be found there with 100% and or maybe 95%, 98% at the peak, and then it will be reduced again. One thing about the probability is important is that finally electron exists somewhere. Yes? Electron doesn't exist here when you go very far because probability density will be vanished also here. But here exists some probability, some probability, some probability. Can you tell me that what is the total probability of the finding electron in the atom? You know, some points has the probability 0.05, somewhere, some distances has a chance to have of the finding electron between these two numbers with this chance. Some of them have very high chance with this number. Some of them doesn't have any chance, or the chance is very tiny. Can you tell me finally the total? Can you tell me finally what is the total probability of the finding electron in the atom? Somewhere electron doesn't exist and somewhere electron exists. So it shows you that the total probability will be 1. And there is another example here which shows the orbitals in the different quantum numbers. And you see that in some case, the probability can be covered by the different probabilities, can be found with different probabilities. Okay, after talking about little about this wave function and those probability business, we'll talk about the penetrating or tunneling phenomenon. This is a phenomenon which happens inside the atoms, only inside the atomic system, and it is very strange phenomenon. You are trying to climb the hill. If you have enough power, you can reach the top of the mountain, as you know. This is only about you or any other classical particles. For the systems which they are quantum mechanical, the situation is different. The quantum mechanical particles can also exist in the region that the kinetic energy is not enough to find the particle there. I mean, if your energy even is not enough to climb the hill, somehow you can enter the mountains by the phenomena which call it tunneling. Yes, and this is happening only in quantum physics for tiny particles, not for real particles. There is some magics, for example, like this guy David Copperfield, who passed from the wall. You remember something like that? Those are not physical. They are fake, actually, all. I want to tell you that there is no any fake tunneling in particle. Particle can reach the top or can penetrate or enter a mountain even if their energy is not enough. And this phenomenon is called quantum tunneling. All right? Quantum tunneling is the phenomena that the kinetic energy is not possible, doesn't make possible for the particle to pass a barrier. But quantum mechanics give this possibility for the particle to penetrate it. Because do you know what is happen? Everything backs to these mathematical diagrams simulation I show you. I mentioned that some place close to the atom have different probability of finding electron. Somewhere you can find electron with 90% certainty. Sometimes you can find electron with 1%. But one thing is doesn't change. The thing is that finally electron exists somewhere. I mean, of course, if you have enough energy, 100% or 99.9%, you can climb this mountain, yes? But there is also a possibility of less than 0.1% that you don't need to climb, you can make a tunnel. And this 0.1% is the number which we need to explain the fusion phenomena inside the atoms, inside the stars. Do you have any question about the tunneling? So tunneling is a possibility for a particle to pass a barrier when the kinetic energy is less than the potential, less than the total energy. This is a graph which shows the tunneling actually. You have a potential energy and you have a kinetic energy. If the kinetic energy below the potential, you know you never can climb. I mean, this dashed line here show you the kinetic energy, yes? Kinetic energy is below than that, yeah? This number is 10, for example, this is 4. With 4, you cannot get 10. That's correct? This is the classical picture. But quantum mechanics change your picture. Quantum mechanics say that this is just about classical systems. Instead of the classical systems, if you have a particle, even with kinetic energy of 4, you can tunnel the potential of 10 and go inside. But the probability of doing this is low, but it's not 0. This is important. Yes? Classical mechanics always say that to pass a barrier, you need a kinetic energy to be enough to pass. Remember here, this picture. But quantum mechanics say no. Even if your kinetic energy is below that, you can pass. But with little probability. I mean, 0.1% is the chance to go through the tunnel. 99.9% of course is to going through that. But this percentage is not 0. It's some tiny number. Do you think this is a fiction? No. The semiconductors worked by this theory. Semiconductivity is explained based off the quantum tunnelings and many other phenomena. Also, quantum tunneling, a type of quantum tunneling also detected before in the lab in 2009 or very recently even, they did some experiments and they already show that this probability of finding the particle can be non-zero even if the total energy is not enough to pass the potential barrier. Basically, as you know, if the total energy is below the potential energy, then the kinetic energy will be negative, and this is not good. You can never have a potential kinetic energy, negative kinetic energy. But quantum tunneling say that no, you can have such possibility, but with lower probability or less probability. Anyway, if you want to little bit understand about the nuclear fusion, you have to know the tunneling. In the picture which we use for tunneling inside the fusion, we consider a two nuclear. One is with atomic number Za, the other one is with atomic number Zb. I mean the number of electron here is Za and Zb for two nuclear. And their mass is Ma and Mab. They have a Coulomb potential, as you know, because they have a charge, so they attract each other. Okay? So the quantum mechanics help you to understand that even if the kinetic energy is lower than the potential, there is still a chance of the electron to pass. It comes from the solving the Schrödinger equations for inside and outside. I mean, think about this like potential you want to pass. So there is an inside and there is an outside. So you need to write Schrödinger equation and solve it for these three parts. If you write the Schrödinger equation and solve, then and write the Schrödinger equation, you end with equation 3.4. The possible solutions for this equation is exponential. Exponential of R gives you a possibility of the solutions for this. And there is a strange things here. There is a parameter here, chi or chi. This parameter actually works like a wave number. If the energy is less than the potential, this chi will be complex number, but non-zero. I mean, you can have a wave functions for here, for right, for left, and for medium levels. But how much will be the chance to find here? It depends to more calculations. If you do more calculation, you can definitely find the chance. The chance of finding the electrons in the places which you never can expect it is given by the equation 3.7. Here, we consider a potential barrier. Look here. You know, R1 and R2 are two distances. R1 is greater, R1 is lower than the R2, but the energy potential for that is greater than the potential energy for this, because potential energy for R2 is this number, potential energy for R1 is here. Yes, kinetic energy is this. You never can get this point by this kinetic energy, but this calculation shows that no, you can get. Even when R1 greater than R2, there is a little chance. This little chance is given here by the psi. The psi gives you the wave function, and this is a little part of the psi. The detail is little complicated. The detail backs to solve this equation for three regions, right, left, and medium, and then matching the solutions. I mean, the solution finally should be matched at the boundary. I mean, when the wave comes here, then want to enter, then want to exit, and again enter this place. So at the exiting point and entering point, or vice versa, the wave function, this PC, should be continuous functions. Never should be changed. I mean, the particle enter here should be here by some chance. Otherwise, it should not be disappear here. This is called continuity. No particle should be disappear. The first person who used this concept to explain the fusion was the George Gamow. So George Gamow was a Russian physicist, and he explained it actually this the nuclear fusion inside the stars. He gave the sun as example and presented that. The book of Birth and Death of the Sun by George Gamow actually gives you the first explanations, one of the first explanations, and to understand the mechanism of the fusion inside the sun. Calculation of the Gamow led to the results. The result was that if we have a potential and this potential energy is function of the R, and if a particle want to reach or pass from this potential, there is a probability for that. Probability of passing a particle with energy E from this potential is given by this expression 3.8. This equation is written in the suitable units and forms. The suitable units is that here, for each energy E, there is a chance to find the electron in the forbidden zone. The forbidden zone is this place. the place you never can expect particle in classical mechanics. Forbidden zone or forbidden city has the probability. Give me the energy E, I will give you the probability. Of course, the probability of finding the electrons or any other particles inside the medium is not very high. I mean, if energy be several times greater than the gamma of energy, then you see that the factor 1 over E will be decreased. To see that, let's to plot this. I wanted to plot the probability. What is the probability? The probability is exponential minus the gamma of energy I take as 1, okay? 1, energy is E over 1 over 2, huh? This is the, and let's X or energy, I mean, change from 0 to 10, for example. If the energy increased, I think I don't, I think I have to check it that I write this correctly or not. Yes, if the energy increase very, very fast, then the chance will be increasing. No, we didn't see this minus factor. So the chance will be increased. Of course, if the particle get more energy, it has a more chance to tunnel. Even it has more chance to reach the potential barrier to the top without using the tunnel. Yeah. But for any other energy, you have this probability. For example, the probability at the X, like 0. This number, for example, is 0.2. But if you change the, I mean, if you go very far, let's to see what happens if I write 10. The probability is 0.7. Do you think this probability will be higher than 1? Anyway, can you reach here higher than 1? Never, never. You know, the maximum will be 0.9. Let's look. I increase the size. Even if you write here 1,000 or 10,000, you see I write here 10,000 or 100,000, then the probability will be 0.996. This is the beauty of quantum mechanics. Probability of finding electron is non-zero, and it depends to the positions. In your situations of the gamma of calculations, for example, if you go far, the probability will increase, but not everywhere. Like in hydrogen atom, you know, it was the situation was opposite. Yes. In hydrogen atom, when you go far, the probability will decrease, but here probability will increase in tunneling phenomenon. So never can exceed it. So if you are curious, you can repeat it, this 1 million. Still, you never can get 1. This is very interesting. You never can get 1. I mean, 1 you can never get, and this is very strange. I mean, it never reach 1. Let's see, you know. Sorry, 100 is very high. For example, you see, it remains always between this, you know, never reach 1. This is the 1, the point. If you click here, you can see that what point is that? Is 1 exactly, or less than 1. The probability is living less than 1, never reach the 1. I mean, never reach this. Sorry, this. Never reach that, you know. This is the ideal case. Ideal is electron exists 100% in 1 point. This is a classical picture. Quantum mechanics say, no, electron exists with different probability in different positions or location or distances from the nucleus. All right. That was my lecture today, because next part is very heavy. I don't want to continue now. I am here. If you have any questions, you can ask me. Otherwise, I will stop the sharing, and then I'm trying to oh, sorry, stop the recording.